Hi, my name is Bill. Welcome to Probability and Statistics for Everyone. And welcome back behind the curtain in my continuing tribute to the movie The Wizard of Oz. In this BTC video too, we will dig deeper into quartiles. This is a direct supplement to main track video 4.2, where we looked at a graphical approach to finding the quartiles of a dataset. In this video, we'll look at some algebraic expressions for finding the quartiles and clear up some avoidable confusion about how to find them in certain cases. To begin, let's return to the example we looked at before. To the right is the combined EDF, dot plot, and box plot of the example data from videos 4.2 and 4.3. The extra dashed lines used in the graphical approach for finding the quartiles are still present. Before we continue, and while we have these plots displayed, let's briefly review. The quartiles are those three values that split the sorted data into quarters. The three values for this data set are shown on the right of the dot plot, where Q1 is the value that splits the data into a lower 1/4 and an upper 75%. Q2, also called the median, is that value that splits the data into a lower 2/4 or half and an upper half. And Q3 is that value that splits the data into a lower 3/4 and upper 25%. On these plots are overlaid four black ovals, one circling the number of points n on the left of the dot plot, and three on the EDF, circling where the 25%, 50%, and 75% cumulative probability values cross the EDF. Those are the three horizontal dashed lines. As we noted before, the 50% value crosses the EDF at a horizontal segment, so we compute the mean of the two endpoints of that segment as Q2. The other two crossings are at vertical segments of the EDF, so we can simply extract the x value of that segment as the quartile. Of course, software like that written to generate these plots and calculate these values doesn't visually inspect a plot for line crossings. An algorithm is needed to calculate the values, and the formulas for that algorithm are now shown on the left. I hope these equations don't unsettle you. They're really not too complicated, but since we're behind the curtain, so to speak, I'm comfortable with presenting them. I did initially include them in main track video 4.2, until I changed my mind, pulled them out, and republished 4.2. I decided that they are a little too complicated for that subset of everyone, which those main track videos are targeting, at least at this early stage. There are three groupings of equations here. Near the top, there are three equations for finding the quartiles when n is odd. It cites the example of n equals 11. But these equations will work for any odd n, 13, 15, 17, 225, etc. We'll have more to say about this case later. Then near the middle are three equations for finding the quartiles when n is even, but half n is odd. It cites the example of n equals 10, an even number, but n over 2 equals 5, an odd number. In fact, the example that we recalled and is currently graphically displayed on the right is for n equals 10. 14, 18, 22 are all examples where n is even, but half n is odd. Finally, near the bottom, there are three equations for finding the quartiles when n is even and n over 2 is even. Or put differently, when n is evenly divisible by 4. It cites the example of n equals 12, but 16, 20, 24, etc. would all work. Let's return to the middle set of equations, since that corresponds to the plots on the right, and explain some of the notation being used. First, as we've noted in other videos, the y's are called the order statistics of the data. That is, they are the set of sorted values. Y sub 1 is the smallest value, y sub 2 is the second smallest value, etc. And y sub n is the largest of the n values we have. Our formula for Q1, then, is to select that single value that is an integerized fourth of the way through the sorted values. We have n over 4, which for n equals 10 is 10 over 4. That becomes 2.5, which is then integerized by the ceiling function. That's what those two upper square brackets mean, where ceiling means to round up to the next largest integer. That leads us to y3, which is what we selected graphically in video 4.2, and that brings us to the value 4.027. Let me also comment about the colors. Typically, I'll try to use black for general or deterministic information, blue for theoretical probability expressions or plots, and red for actual data or functions of that data. That's why 10, 2.5, 3, and 4.027 are in red. I won't be absolutely precise about this, but it will be my usual approach. By the way, that's why these plots are red. Next, let's move back up to the case where n equals 11, which is now displayed graphically on the right. It isn't easy to see because of how this random data set aligns, but the 25%, 50%, and 75% probability values, again, those three horizontal dashed lines, cross the EDF at vertical segments, indicating that the quartiles are to be selected directly from the data values, with no averaging of adjacent values needed. And that's what the highlighted equations on the left do. And that's it. It's that simple and straightforward. Unfortunately, we need to pause for a comment here. Some well-meaning instructors suggest that one way of finding the lower and upper quartiles is by splitting the data in half and finding the medians of each half. Attempting to do that when n is odd leaves an apparent dilemma of whether to include the full data median, called Q2, in both halves or in neither half of finding the medians of the halves. Some theoreticians would lead one to believe that this is an arbitrary decision. Nonsense. When dealing with an odd number of values, the centers of the halves may not be the quarters of the full. And if you go back to the definition of what quartiles are supposed to do, they're supposed to divide the data, the full data, into quarters. The graphical approach on the right and the algebraic expressions on the left will always accomplish that and produce results that are consistent with each other. Think about it this way. It's always true that if the 50% value crosses the EDF at a vertical segment, which will always happen if n is odd, then the 25% and 75% values will also. Enough on that. Let's move on. We'll move back down to the bottom case where we have 12 samples. As we noted, this is an example where n is evenly divisible by 4. And the result is that all three quartiles are to be calculated as means of two adjacent samples. That's what the equations on the left do, and that's what the three horizontal crossings in the EDF indicate. On this particular plot, horizontal segment at the 50% level is so narrow that it's hard to see, but it's there. Now I think I've said all that needs to be said about quartiles. I didn't want to bog down video 4.2 with some of these details, but it's important that I present them to you somewhere, and here was the place. And that brings us to the end of this Behind the Curtain, or BTC video. Keep checking back, as there will be more videos to come.